Hello, everyone. My name is Klaus Rudolf Klatny, and I'm excited to present to you our iClear paper called Conformal Generative Modeling with Improved Sample Efficiency through Sequential Greedy Filtering. Generative models, and specifically large language models, are widely known to be susceptible to hallucination. For a given input, such as this chest X-ray image, the model predicts a factually incorrect response. And as such, employing generative models in fields such as medicine constitutes a safety hazard. In the present work, we develop a new calibration method called Sequential Conformal Prediction for generative models, or ScopeGen for short, that ensures rigorous statistical guarantees such that generative models can be safely deployed in practical applications. The goal of our method is to satisfy a guarantee that we call conformal admissibility control. Our method generates so-called prediction sets, which are sets of artificially generated responses. We say that a calibration method fulfills conformal admissibility control if it generates prediction sets that are admissible with high probability. And in turn, a prediction set is called admissible if at least one of its elements is admissible. So in the example right here, the prediction set at the top is inadmissible, while the one at the bottom is admissible. ScopeGen is based on conformal prediction, which has a rich history in the field of machine learning. It's typically applied in low-dimensional regression or classification settings, such as the one shown here. We generate a prediction set by including all labels in the prediction set whose nonconformity is lower than or equal to a given threshold that has been estimated from calibration data. And it can be shown that conformal prediction fulfills the guarantee that the true label for an unseen image is included in the prediction set with probability greater than or equal to 1 minus alpha, where alpha here is a user-defined confidence threshold. Unfortunately, conformal prediction is not straightforward to apply to generative models, and this has the following two reasons. The first challenge is that conformal prediction makes a guarantee in terms of exact coverage, which is not really suitable. For instance, we look at these two sentences right here. The heart is enlarged, and there is heart enlargement. While these sentences are semantically equivalent, they don't match exactly, and this is something that conformal prediction cannot take into account out of the box. Second challenge is that conformal prediction would require evaluating a nonconformity measure over the entire output space of the generative model, for instance, all possible token sequences of a fixed length. And I think it's needless to say that this is computationally intractable. The first challenge can be relatively easily solved by relaxing the coverage notion to admissibility, and it's been done similarly in related works. So instead of considering an exact match between generated Y and ground truth Y, we only require them to be similar as measured by an admissibility function here denoted by A. And for the second issue, this is where ScopeGen really comes into play. Instead of applying conformal prediction to include elements from the output space of the generative model, we use it instead to count how many times a specific sampling operation needs to be performed. So to generate an initial prediction set, we first begin by generating IID samples from the model until the value of a nonconformity exceeds a given threshold that's been calibrated via conformal prediction. Typically, we then also have certain prediction set desiderata, such as high quality and diversity, which we address via sequentially filtering out examples by subsampling the previous prediction set in a specific order that is here indicated by the numbers in the purple circles. For instance, if we want to filter out low quality examples, we subsample the element with the largest quality value from the previous prediction set. And in order to filter out similar examples, we use furthest point subsampling. And just as in the generation stage, we repeat the sampling operation until the nonconformity value exceeds the calibrated threshold. So we have 3 calibrations in total, and if we then distribute the risk budget alpha across these 3 steps, we have conformal admissibility control at level alpha for the final prediction set. We see in our experiments that ScopeGen performs favorably in comparison to this existing method by Victor Quack et al. Across a variety of data sets and metrics. Specifically, ScopeGen excels in the amount of admissibility queries required during calibration and also calibration runtime. With that, I'm happy to conclude. Feel free to check out both our paper and code. And thank you very much for listening. Have a great rest of your day.